Tim van der Zee from the University of Amsterdam, and he has a 5-minute talk. Take it away.
Thanks. So can everybody hear me? Okay, my name is Tim, and I'm going to talk about the question, does metabolic power increase with force rate? So as we heard in the previous presentation, metabolic cost seems to be important for human movement, including walking. And I think there's a lot of people in the audience that would like to be able to accurately predict metabolic power, which could be beneficial for understanding movement, improving rehabilitation, and designing assistive devices. But it seems to be quite difficult to accurately predict it. So, well, we know that there's a cost of work and a cost of tension time, but these two costs don't seem to be able to accurately predict the cost associated with intermittent force. And that is because studies have shown that intermittent force is more costly than constant force, even when the average is the same. And when the average is the same, the tension time does not predict a difference. But also when the contraction is isometric, and then cost of work won't explain this difference. Also, higher frequency intermittent contractions have been shown to be more costly than lower frequency intermittent contractions. And we think that this has something to do with calcium dynamics. So calcium is needed to expose the binding sites on the actin filament, such that the myosin head can attach and perform the power stroke, which is needed for force. And afterwards, calcium needs to be pumped back to the sarcoplasmatic reticulum, which costs metabolic energy. And we speculate that with a higher frequency of the intermittent contractions, there is an increasing overshoot of calcium, such that more calcium needs to be pumped back, and therefore more metabolic energy is required. And we also speculate that the underlying factor is increasing in average absolute force rate with the increase of frequency of the intermittent contraction. But studies so far only have been done with isometric contractions and electrostimulation, which is different from submaximal voluntary activation. Or they have done with submaximal voluntary activation, but then with dynamic tasks like leg swinging and human walking, which have a substantial amount of positive mechanical power. And therefore with this task it's difficult to know whether the cost is due to cost of work or cost of force rate. So therefore, we thought of an experiment in which subjects delivered torque against a dynamometer, which was fixed at a constant angle, such that muscle contraction was isometric and work was small. And the subject delivered this knee extension torque with both legs simultaneously, while we measured the joint torque with the biodex, metabolic power with COSMAT, and we did also some muscle imaging with the ultrasound to get an estimate of fiber length change and thereby work. So here's a typical example of torque during 3 different conditions that differed in frequency, but were the same in the average torque. And here we see that force rate, or actually average absolute force rate, indeed increased with the frequency of the torque time series. And this is our main result. So on the vertical axis is metabolic power shown in watts per kilogram. And on the horizontal axis the frequency, and all subjects showed an increase of metabolic power with the frequency. And this was not explained by tension time because average torque was the same. And it was also not explained by cost of work because this task was isometric, such that the amount of work was really small. And the amount of work was estimated using simulations with a Hill-type muscle model, but also with ultrasound measurements. And then because force rate increased also with frequency, the fit improved substantially when force rate was included. So therefore take-home message is that intermittent contractions require a substantial amount of metabolic power compared to constant contractions. And the total metabolic power is explained by summing cost of work, cost of tension time, and cost of force rate. So we think including force rate into predictions of metabolic power is important. And that's my presentation. Thank you for your attention. Would like to thank the funding. Are there any questions?
And as we take questions, could we have the next speakers set up? Here you go.
So I wasn't clear on how you were, I saw you using COSMAT to estimate metabolic power, but the time horizon seemed very short. for estimating? Because usually it takes humans a little while, 3 to 4 minutes to get to steady state. At least that's in walking. So you can clarify that.
Yeah, it's a good question. Every condition, and then I mean like a certain frequency of the torque time series, was 6 minutes, and metabolic power was averaged over the last 3 minutes of this 6 minutes.
Other questions? I have one. Do you think for like an athlete, like a sprinter, if they could have quicker calcium recovery, it would give them a competitive advantage?
Well, for sprinters, I think in general metabolic,
It's
it's
a
not
high
really
frequency
important to have
activity.
a low metabolic power because it's more about mechanical power, I think.
How about a ping pong player?
A ping pong play. Yeah, I think a ping pong energetic is not really important. But yeah, maybe for a marathon runner, it would be beneficial to keep metabolic power low, such that you have a high economy in there. That could maybe be done by efficient calcium dynamics. Yeah.
All right, Andy.
I can imagine the converse experiment where you keep the force constant, but you fluctuate the velocity, or you fluctuate position versus time. So you call it's a force rate cost, but that's in your particular cross-section of the force velocity landscape. If you did a different cross-section where you kept the force constant, but you fluctuated the velocity at different frequencies, or position at different frequencies, do you think you get no frequency dependence?
But then, yeah, then it's a totally different question because
It's the same question, it's just a different cross-section. I guess I'm questioning because in your experiment, the control was force rate, doesn't mean that it's force rate.
Yeah. So what you're saying, you keep the force constant,
Yes.
but then you don't have a force rate cost, but you think you have a calcium cost?
I don't know what the mechanism is, but you could just do a different experiment where you hold the force constant, but you fluctuate the velocity.
Actually, I've done sort of an experiment like this in which I kept the force constant and I played a little bit with the velocity. So yeah, you could do this and compare it. It would be interesting. Yeah.
Okay, we need to keep moving, so let's thank our speaker one more time.